There is a question that has been quietly circling the energy industry for over a decade. It is not about whether green hydrogen works. The chemistry is settled, the technology exists, the engineering is proven at small scale. The question has always been the same question: who pays for it first? Every serious analyst looking at green hydrogen eventually arrives at the same bottleneck. The economics only work when the equipment runs nearly all the time, when buyers are locked in for years, and when the price of clean electricity is low and stable. Getting all three conditions to align has been the central challenge. Policy frameworks have tried. Government subsidies have pushed demonstration projects into existence. But bankable, profitable, self-sustaining green hydrogen at industrial scale has remained just beyond reach. Until now, the models assumed that climate policy would create the demand signal, that regulation would force industries to decarbonize, that mandates would unlock contracts, and that contracts would unlock capital. It is a logical sequence. It is also slow, and it depends entirely on the political will of governments that change every 4 years. What if there is a different pathway? What if the entity that finally creates the demand signal that makes green hydrogen bankable is not a government agency, but a technology company trying to keep its servers online? AI infrastructure is expanding faster than electricity infrastructure. Data centers are being permitted, funded, and built on timelines that grid interconnection queues cannot match. That mismatch is new, it is accelerating, and it creates something that hydrogen developers have rarely encountered from a single customer class: urgency. Urgency creates willingness to pay, and willingness to pay is what changes energy economics. Artificial intelligence has changed many systems in a very short time. Most of the conversation about that change has focused on software, on what AI can generate, predict, or automate. But there is a physical layer to this transformation that rarely makes headlines, and it is already straining infrastructure built decades ago. Training a large AI model requires extraordinary quantities of electricity. Running that model at scale, serving millions of queries per day, requires more. The data centers that house these systems are not ordinary office buildings with servers in the basement. The largest AI facilities consume electricity at a scale that rivals mid-sized industrial operations. Some of the hyperscale campuses under construction today will draw power comparable to small cities, continuously, around the clock, year after year. That load profile is unusual. Most industrial electricity consumers have variability. A steel mill ramps up and down. A factory has shifts. A commercial building has daily peaks and overnight valleys. AI infrastructure does not work that way. The inference engines that power large language models, recommendation systems, and real-time analytics need to run constantly. Demand does not fall at 2 a.m. It does not drop on weekends. It does not respond to price signals the way traditional consumers do. The load is continuous, dense, and growing. Utilities were not designed for this. The grid interconnection process in the United States, the formal queue that new large electricity consumers must join before they can connect, has become severely congested. Some projects are waiting 5 years or more for interconnection approval. Transmission infrastructure, the physical lines that carry power from generators to load centers, was built for a different pattern of demand. The mismatch between where AI data centers want to locate and where the grid has spare capacity is growing into a genuine constraint on the industry's expansion. Technology companies building AI infrastructure are not passive observers of this problem. They have large capital budgets, long planning horizons, and strong financial incentives to solve it. And they are beginning to look at the problem the way that industrial planners look at it. Not as a policy problem to be solved by regulators, but as a supply chain problem to be solved by engineering and contract structure. To understand why this matters for hydrogen, it helps to understand what uptime means in the context of AI infrastructure. A data center that supports consumer software can tolerate occasional outages. Users are frustrated, engineers scramble to restore service, and the company absorbs some reputational cost. That is unpleasant but manageable. But a data center running continuous AI inference at industrial scale, processing financial transactions, running logistics systems, operating in environments where milliseconds of latency translate directly into revenue, faces a fundamentally different calculus. The cost of interruption is not measured in user complaints. It is measured in direct financial loss, contractual penalties, and competitive disadvantage. This is why the concept of firm power has become increasingly important in discussions of AI infrastructure energy. When electricity cannot be guaranteed from the grid, companies start looking for energy they can store. Energy that can be produced when supply is abundant and deployed when reliability is critical. That search leads eventually past batteries and into a conversation the industry had not expected to be having this soon. Firm power means power that is available on demand, continuously, regardless of what the wind is doing or whether the sun is shining. It means power that does not go away during a grid stress event, a heat wave that pushes system-wide demand to record levels, or a transmission fault 3 states away. It means power that the facility can count on in the same way it counts on its cooling systems and its network connections. Renewable energy, as it is typically procured, is not firm. A power purchase agreement with a wind farm gives a data center access to clean electricity on average, across hours, days, and seasons. But on any given hour, the wind may not be blowing. The grid can compensate for this variability through a complex system of reserves, but that compensation becomes harder and more expensive as more variable generation is added to the system and as demand centers become more rigid. Batteries help. When electricity must be guaranteed rather than predicted, storage duration becomes more valuable than storage efficiency. That distinction matters enormously. Lithium-ion storage has improved dramatically in cost and capability, and large battery systems can smooth out variability over periods of hours. But a battery that can power a large data center for 4 hours is a very different proposition from one that can power it for 4 days. The physics of battery storage do not scale economically to multi-day or seasonal backup. For short interruptions, batteries are excellent. For extended outages, grid stress events lasting days, or seasonal mismatches between renewable generation and demand, something else is needed. Hydrogen provides something batteries cannot. When green hydrogen is produced by an electrolyzer running on renewable electricity, that energy can be stored indefinitely in tanks, in pipelines, in industrial quantities, and converted back to electricity through a fuel cell when it is needed. The round-trip efficiency is lower than a battery. The cost per kilowatt-hour of storage is higher for short durations. But for long-duration backup, for the kind of resilience that means a facility can operate independently of the grid for extended periods, hydrogen becomes cost competitive with alternatives, and in some scenarios there is no realistic alternative at all. A fuel cell connected to a hydrogen storage system can provide continuous, clean, reliable power for days. It can operate in a parking structure or a rooftop installation. It does not require combustion, it produces water vapor as a byproduct, and it does not depend on grid availability. For a data center that needs to maintain 99.99999% uptime, 5 nines, which means less than 6 minutes of downtime per year, that capability has a value that is difficult to express in purely per kilowatt-hour terms. Green hydrogen has an economics problem that has proven stubbornly difficult to solve. The levelized cost of hydrogen, the full cost of producing 1 kilogram including capital, operating expenses, and electricity, remains significantly higher from green sources than from natural gas reforming. The gap has been closing, electrolyzer costs have fallen substantially. Renewable electricity prices in favorable locations have dropped to levels that make the math increasingly interesting. But the gap is not yet closed enough to make green hydrogen competitive without some form of subsidy or premium market in most applications. What the economic models consistently show is that cost depends enormously on utilization. An electrolyzer that runs at 40% of its capacity because the renewable electricity source is intermittent produces hydrogen at a much higher cost than one that runs at 80 or 90% capacity because it has a continuous power source. Every hour the electrolyzer sits idle, the capital cost of building it is spread across fewer kilograms of hydrogen, pushing the cost per kilogram up. This is the capacity factor problem, and it has haunted green hydrogen economics for years. Put plainly, hydrogen is not only expensive because the technology is immature, it is expensive because the equipment is often idle. That idleness is not an engineering failure, it is a demand failure. AI infrastructure changes the idle time assumption entirely. It is also notably a problem that a reliable, continuous electricity buyer can help solve. If a green hydrogen project is co-located with a large electricity demand center, or if the electrolyzer is powered by dedicated generation that runs at high utilization because it serves a continuous load, the capacity factor problem becomes much more manageable. An electrolyzer that runs at 85% capacity, powered by clean electricity purchased at a stable long-term price from a creditworthy counterparty, produces a financial model that looks very different from one subject to the variability of merchant power markets. AI data centers as a class of energy buyer tick several of the boxes that hydrogen project developers have historically struggled to find. They are creditworthy. Technology companies with large AI operations have strong balance sheets and access to capital markets. They sign long-term contracts. Infrastructure decisions made by major technology firms typically involve multi-decade planning horizons. They have predictable demand. The load profile is continuous and does not vary dramatically with economic cycles. And they have a direct financial interest in reliability, which means they are motivated to pay a premium for firm, clean power in a way that a commodity buyer is not. This changes the project finance conversation. When a hydrogen project developer approaches a lender with a signed offtake agreement from a creditworthy buyer who has committed to purchase a fixed quantity of hydrogen or clean electricity generated from hydrogen at a fixed price for 20 years, the risk profile of that project is fundamentally different from one that depends on spot market prices. Lenders understand creditworthy counterparties. They understand long-term contracts. They price risk accordingly. And lower financing costs directly reduce the levelized cost of hydrogen. This is the insight that most hydrogen adoption models have missed. Hydrogen may scale first, not where emissions reduction has political value, but where reliability has financial value. Those are different maps, different customers, different timelines. And the second map may move considerably faster than the first. It would be a mistake to suggest that this dynamic applies everywhere or that the transition from insight to infrastructure is simple. There are real constraints on where green hydrogen projects co-located with AI infrastructure make economic sense, and understanding those constraints is part of understanding the opportunity. The geographic and logistical conditions that favor this model are specific. Areas with strong renewable resources, high wind capacity factors in the Great Plains, high solar irradiance in the Southwest, offshore wind potential along the Atlantic coast, provide the low-cost clean electricity that makes the electrolyzer economics work. Areas where grid congestion is most severe are the same areas where data centers are increasingly looking for alternatives to central grid power. These maps do not perfectly overlap, but they overlap more than they once did. And the overlap is growing as AI infrastructure expands beyond the traditional coastal data center corridors. Industrial clustering also matters. A single large data center consuming substantial electricity is an interesting customer for a hydrogen project. A campus of data centers co-located with other industrial loads, connected by a private microgrid architecture, and anchored by a shared hydrogen storage system becomes something more structurally robust. The more load that can be aggregated into a stable, continuous, predictable demand profile, the better the economics for the hydrogen infrastructure serving it. The integration model that emerges from this logic is not a simple power purchase agreement. It is an integrated energy system in which on-site renewable generation, solar, wind, or both, powers an electrolyzer that produces hydrogen during periods of high generation. That hydrogen is stored on site. When generation is insufficient to meet load, or when a grid outage requires the facility to island from external power, fuel cells convert the stored hydrogen back to electricity. The result is a facility that can operate at high reliability from predominantly clean sources, with a significantly reduced dependence on grid power quality. If this model proves successful, if even a handful of AI infrastructure projects in the next several years demonstrate that green hydrogen systems can be financed, built, and operated profitably on the basis of technology company demand, rather than government mandate, the implications extend well beyond data centers. The demonstration effect in energy infrastructure is powerful. The cost curves that matter are not just the engineering cost curves for electrolyzers and fuel cells. They are also the learning curves that come from building projects, solving integration problems, training workforces, and developing supply chains. Every project that gets built teaches the industry something that the next project can use. Every project that achieves bankable economics reduces the risk perception of the ones that follow. Industrial clusters in other sectors, chemical manufacturing, steel production, heavy logistics, port operations, have been watching green hydrogen economics with interest for years. Many of them need firm, clean power in the same way that AI data centers do. Many of them have the demand consistency and the creditworthiness that hydrogen project developers need. The difference has been that they have not had the same urgency. They are not paying millions per hour when their operations go down. They are not under the same competitive pressure to secure energy reliability at almost any cost. AI infrastructure provides the urgency. It provides the first customer class willing to pay the premium that makes early green hydrogen projects profitable. And profitable early projects are how industries reach the scale that brings costs down for everyone. But consider what happens if the grid does not catch up. What happens if interconnection timelines remain slow? If transmission investment continues to lag load growth? If electricity price volatility increases as variable generation penetration rises? In that scenario, hydrogen does not remain a climate technology waiting for political support. It becomes an infrastructure hedge, a structural solution to a structural problem. And infrastructure hedges attract a different kind of capital than clean energy projects do. The pathway that most hydrogen adoption models have assumed, policy, then subsidy, then pilot, then scale, is not wrong. It may still describe how hydrogen expands into hard-to-decarbonize sectors over the next decade. But it is slow, and it is dependent on political conditions that cannot be controlled. The alternative pathway, reliability requirement, then guaranteed demand, then bankable contracts, then scale, is faster, more durable, and requires no political consensus to move. The question for developers, investors, and infrastructure planners who are watching this dynamic is not whether it is real. The electricity demand from AI is real and growing. The reliability requirements are real. The project finance logic is sound. The question is how to position for it. Understanding hydrogen project economics at the system level, capacity factor sensitivity, LCOH drivers, microgrid integration, storage sizing, offtake contract structures, is the foundation. The opportunities in this space will not go to the parties who understand only the technology or only the policy environment. They will go to the parties who understand how all of these systems interact, how the economics respond to changes in input assumptions, and how to structure projects that can attract capital in the financing environment that actually exists. That is not a trivial level of understanding. Hydrogen systems are complex. The integration of electrolyzers, storage, fuel cells, and renewable generation into a coherent infrastructure system requires careful engineering and careful financial modeling. The contractual structures that make these projects bankable are not standard templates. The regulatory environment varies by jurisdiction and is still evolving. The supply chains for electrolyzer components and fuel cell systems are still developing. None of this is insurmountable, but navigating it requires genuine expertise. The companies and developers who build that expertise now, who understand not just the headlines, but the actual system economics, the actual project structures, and the actual pathways to bankability, are the ones who will be positioned to act when the window opens. And based on the trajectory of AI infrastructure investment, that window may open sooner than most hydrogen timelines have assumed. If grid expansion continues to lag electricity demand, reliability becomes a premium service rather than a baseline assumption. The parties who understand how to deliver that premium and how to finance the infrastructure behind it will not be waiting for the policy cycle to turn. The history of energy transitions is not primarily a history of good intentions. It is a history of economic necessity, meeting technical readiness at the right moment. Solar power did not scale because the world decided to scale it. It scaled because the cost fell to the point where it was cheaper than the alternative. And once that threshold was crossed, deployment accelerated in ways that surprised nearly every forecast. Green hydrogen may be approaching its own version of that threshold, not through the slow accumulation of policy pressure, but through the sudden clarity of a demand signal from an industry that cannot afford to wait. Artificial intelligence needs power. It needs reliable, continuous, firm power. And it is willing to pay for it in ways that change the economics of everything upstream. Here is what makes that signal durable. AI is not intentionally building the hydrogen economy. It is simply demanding reliability at scale. Hydrogen happens to solve part of that problem. That is a more stable foundation than a subsidy regime that can be reversed, or a carbon price that can be legislated away. Economic necessity does not change with election cycles. That is not a climate story. It is an infrastructure story. And it may be the most important story in energy right now. For developers, consultants, investors, and infrastructure planners building expertise in hydrogen project economics and system-level integration, Visit H2 Hub, the platform for navigating the commercial realities of the hydrogen transition.